Hello class! Today we're going to be looking at exponential growth and decay. There's a very specific model, a formula for that we're going to learn and then apply it to situations. So obviously the growth model is going to be rising and the decay model is going to be falling. Oops. All right. We are going to show you what that growth and decay model formula looks like. A is equal to A sub 0 times E raised to K T. Now, we do need to tell you what all those letters mean. So, the first A without anything there. The ending amount the A sub 0 is for the initial amount. And when K, remember E is just that constant, when K is greater than 0, we are experiencing a growth model. When K, which is a constant, is less than 0, it is a decay model. And this is a constant rate and we're going to measure that in decimals, not a percent, just like we did with our interest rates. And then T is going to be time. That time could be measured in minutes, weeks, hours, days. I mean, that is just dependent. So whatever we're doing, we need to make that consistent through our problem. All right, that's supposed to be a K. There we go. So let's take this formula and start applying it to some models. Our first model says that in 2000, the population of Africa was 807 million, and by 2011 it had grown to 1,052 million. So we're going to use that growth model, A equals A sub 0, E raised to the KT, in which T is the number of years after 2000. And we want to find the exponential growth function that models that. So what we're really looking for, we have a beginning and an end, and we have the amount of time. What we're looking for is the K. So what we have A is our ending amount, which is 1,052 million. Our A sub 0 is 807 million. Our time is 11 years after 2000, so it's 11. And our K, we don't know that. That's what we're finding. So we're going to set this up using this model. 1,052 is equal to 807 times E raised to the K times 11. Now E is a constant. Remember that we can find that on our calculator. K is what we're looking for. So the first thing I'm going to do is divide each side by 807. And I'm going to keep it just like that. These cancel. So we have 1,052 over 807 equals E raised to the K times 11. I'm going to rewrite this as a logarithmic equation. Now log base E is the natural log. So it's going to be the natural log of 1,052 over 807 is equal to 11 times K. So if I want K by itself, I'm going to divide this by 11 on both sides of the equation. So I divide that, and I'm going to put this into my calculator. So that K equals, and our calculators can handle this all at once, and that equals 0.024. That's not what they asked us for. They want to find the model that does that no matter what year, how many years. So it's going to be A equals A sub-zero times e raised to the 0.024 t. That's what they're looking for. So now that we have found that formula, we can use that to answer another question. And this one is, by which year will Africa's population reach 2 billion, or we're going to use 200 million. So our ending is going to be not 200 million, 2,000 million, 2,000. And once again, our beginning is going to be the 807 that they had in 2000. And our k, which we found last time, is going to be the same because it's a constant of 0.024. And what we're looking for now is the time. So we're going to set this up. 2000 is equal to 807 times e raised to the k, which we found is 0.024, times t. We're going to solve this very similar. This time, though, we're looking for t. So first thing we do, divide by 807. That cancels these out. Then we want to write it as a logarithmic equation. So log base e is the natural log of 2,000 over 807. And that's going to equal 0.024 t. So to find t, we're going to divide by 0.024 on both sides of the equation. And that cancels those out. When we put this into the calculator, we're going to find that t is 37.8. Well, let's just round it to the nearest year, 38. That's not the year 38. Remember, that's the number of years after 2000. So we're going to add that on to 2000. And we get the year 2038. So let's move on to another word problem or real-life application. Well, strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. Now, the half-life of strontium-90 is 28 years, meaning that after 28 years of a given amount of the substance, it will have decayed to half of its original amount. So we want to find the decay model for strontium-90. So our original amount, our ending amount, our original amount. We're just going to start out with 100%, or 1. Our ending amount after 28 years is going to be 1/2 of that, or 0.5. We don't know how long or what the constant is. That's what we're going to try to find so we can create the equation. And our time for that half-life is 28 years. So our ending amount, 0.5, is equal to 1 e times k and times the time of 28. We're going to do this the same way we did before. Put this in a logarithm equation. So the log of base e is the natural log of 0.5 is equal to k times 28. So we'll divide by 28, and that's going to give us k. So we'll put that in our calculator, and we get k is negative 0.0248. Hey, it makes sense that that's negative because it's declining or it's decaying. So our formula then is going to be A equals A sub 0, E raised to negative 0.0248 T. 0. There we go. So let's apply that formula that we just found in this situation. Suppose that a nuclear accident occurs and it releases 68 grams of strontium-90 into the atmosphere. How long will it take strontium-90 to decay to a level of 10 grams? So our ending amount is going to be 10. Our beginning amount is 60. And our K, which we found the last time, was negative 0.0248. And this time we're looking for the T. So we're going to put this together as 10 equals 60 times E raised to the negative 0.0248 t. Once again, solving the same way we've done all through this lesson. Let's divide by 60. Those cancel out. Let's write it as a logarithm problem. So the natural log of 10 over 60, or 1/6, is equal to not e, because we're writing this as a logarithm, negative 0.0248t. So we're going to divide by that negative 0.0248 on both sides of the equation, because that gives me t on this side. Oops, there we go, t. So we'll take this and put it into our calculator and find that t is equal to about 72 years.